So, in the previous lecture we looked at the superposition of a source and uniform flow, and the kind of flow pattern that we derived, and specifically the shape of the body for which that flow is applicable was actually what is called as a half Rankine solid. So, we saw how this flow pattern emerges out of this simple superposition, and then we also looked at the pressure distribution. How do we determine pressure distribution on the surface of this solid, typically the psi 0 streamline. So, we will extend this discussion here today, and we will look at three specific topics in that sense. We will look at the method of images, and I will talk about what this method is. Then I will extend this idea of getting a pressure distribution and then applying it to calculate forces on a solid object or on a body that is immersed in a potential flow, and then finally I will talk about, as a consequence of the force of what the force distribution looks like, I will talk about the Blasius theorem. Alright, so let us begin today's lecture. So far we have looked at superposition of elementary flows, and the kind of flows that we have looked at, just to bring your attention to them again, we looked at how when we superpose a source and a sink which are very near each other, okay, and near the origin, we could derive a doublet, right. So, we got a doublet out of this superposition. Then we also saw that if we have a uniform flow and there is a doublet at the origin, then we got flow over a cylinder. So, this is plus a doublet gave us flow over a circular cylinder, right. And we also saw, as I was mentioning in the last lecture, we looked at what happens if you have uniform flow added with a source, right, and we got a Rankine half solid. So, we looked at these three scenarios. Now, there is something common about these three, and the thing that is common in these three situations is that these are actually flows which can be classified in the category of unbounded flows. What I mean by that is that there is no physical boundary which is holding these flows, or which is sort of confining these flows in a certain domain or in a certain specific region. Now, in most practical problems that we encounter, we typically have the presence of a rigid boundary, okay, which constrains the flow in a specific zone. So, in those cases where the flow is not unbounded, rather it is bounded, we rely on this method of, which I call as method of images. And I will give you some illustrations of how this method is going to work. So, let us take an example. Okay, so, let us take an example of the following type. Say we have a wall, a rigid wall, a horizontally inclined rigid wall, okay, and I have a source, let us say of strength m, which is located at some distance from this wall. The question that I am asking is, what kind of flow patterns would we expect when we have this scenario? Now, notice that if there is a single source, then the flow will flow out radially. But the only issue now is that if the flow goes out radially, there is a wall which sort of constrains the flow. It doesn't allow the flow to go through. It's a physical boundary, a physical barrier. So how do we do this now? How do we model this? So the thing that we exploit in such situations is that the wall being a physical boundary and typically a stationary wall, it basically means that the normal velocity or the velocity component or velocity dotted with the normal component on the wall is 0, right, on this wall. So if I say uw dot n cap, this is 0 on the wall because there is no penetration through this wall, and the normal vector is basically, let us say this is the normal vector. So clearly if this is the case, then I could say that this wall surface is a streamline. After all, that is how we define a streamline, right? It's a line across which there cannot be any fluid flow. So the method of images exploits this idea, and the way it exploits is with this illustration we can do it again. So instead of putting a wall there, let's say, let me define this wall by a dotted line or by a dashed line. Okay, so let's say this is surface AB, and I define my source at the same distance, which is say h from the wall. But what I do is at an equal and opposite distance and using the wall as a mirror, which means at a distance h on the bottom half, I put another source. So let us consider this as an example. Now having two sources and one being an image. So let me say this is an image source and this is that one is a origin source. So having this situation or having these two sources at equal distance ensures that the entire wall or the surface AB, I should say surface AB, has u dot n cap to be 0. This you can work out just by superposition of these two sources. Now you can work out that the surface AB will always have this, will always satisfy this condition as long as the sources are of equal strength and the distances from the surface are the same. So you see now that the wall could be replaced by this new scenario. So we have replaced the original problem with a modified problem, which is an unbounded problem, by the way. This is an unbounded flow, but we now know that the method that we followed is that we convert the bounded flow problem into an unbounded flow problem by using an image of the original elementary flow. Okay. So we get the y component of velocity. If I define x and y here in this fashion, then v is 0 on this surface AB. Now similarly we can do even for a vortex. So say we have a vortex near a wall. Okay, so say we have a counterclockwise rotating vortex of strength gamma at some distance, say h from the wall. Okay, so this is the wall and I want to derive the resulting flow field. Well, again this is a bounded flow problem, but I can easily replace this with an equivalent problem by using the method of images, by taking a surface again which is a mirror surface, maybe again AB, placing the vortex, original vortex right in its original position, which is gamma at some distance, same distance h, but right underneath it, and that means under the surface AB and at the same distance h, I can put another vortex to cancel out the effect of putting another vortex at the bottom and to get the surface AB as a streamline. Now it is easy to see here that even though in the original case I put a source and a source to get a 0 velocity on surface AB, here we have a counterclockwise vortex. So the vortex that I have to put on the image point this is the image point, right. This is the image where I have to create it. We have to create another vortex. I would put a vortex of equal but opposite rotation. So, we will have to put a vortex of strength gamma, but in the clockwise direction. That will ensure on the surface AB you do not have any y component of velocity. Alright. So, this is what the method of images broadly looks like, that we counter, we create, we remove the physical boundary, but to remove that boundary and to ensure that that boundary remains a streamline, we create additional elementary flows which give us a desired effect. Okay. So, this is all that I wanted to say about method of images, and maybe in one of the problem solving sessions we will take up an example of how to work this out. Okay, now let us look at forces on a two dimensional body. Okay, so, we have now derived the velocity field and the pressure distribution on any surface, and you should now be able to say a lot about what kind of forces does a body feel or would a body experience. So, mainly we are looking at lift, which is the vertical force, and drag, which is a horizontal force. Okay. And these will be forces per unit depth, as we are only dealing with a 2D representation of any physical 3-dimensional object. Now, the thing that we are going to work out is that these lift and drag forces for any arbitrary shaped, for any arbitrary cross section body, these lift and drag can be obtained using the Blasius theorem, which we will eventually now derive in this lecture. And to give you some idea, this Blasius theorem is a theorem by which the force is related to the velocity distribution. Okay. So, the force is related to, in our case, as I will show you, it would be related to complex velocity on the surface of the solid. So, how do we determine this force, and then eventually we will get to what is the Blasius theorem. So, let us take a stationary 2-dimensional solid, okay, with some arbitrary cross section. So, there is no particular preference for me, but let us say this is a solid far away from which we have uniform flow. Okay. So, this is uniform flow which is far upstream, and we could have any sort of combination of elementary flows along with uniform flow. Okay. So, this solid is stationary, it is not moving, and the part we are concerned about is what is the hydrodynamic force on this solid because of flow going past this body. Okay. So, say we define our coordinate system, we say this is y, this is x, probably the origin we can keep inside, it does not matter. We can say that we are looking at calculation of the drag force D and maybe the lift force L on this solid because of flow going past this solid. Alright. Now, if the force on the solid is, as I said, if the lift force is L, the drag is D. So, I can say the force on the solid, the subscript S denoting solid, is D I cap plus say L j cap, right, that we can say is the force on the solid. By Newton's third law, clearly the force on the fluid, let us say F f, would be equal and opposite. So, we can say force on the fluid would be minus d I cap plus L j cap. So, that makes it a little easier now. Now that I have force on the fluid, I can use some principles or some theorems from fluid mechanics to correlate the velocity, field and pressure with this force. And the way to do it is we use control volume analysis. So, say I take a control volume of, for now, any arbitrary shape, say this is the contour C which encloses this control volume. Okay. So, this is a contour in 2D. Okay. And we can then write the momentum conservation equation for the fluid in this control volume. So, we can write momentum conservation equation, and we will write it in a general form, right. So, we can say this will be the volume integral of rho being the density of the fluid, du dt, where u being the velocity, dv, and I am going to use vectorial notation for a little while, just because it will make it easier for you to understand, as I am sure all of you have done some level of fluid mechanics at your undergraduate level, and you would be familiar with the vectorial form of writing these equations. So, we will say it is rho du dt dv plus the surface integral S of rho u dot n times vector u into ds. This should be equal to the sum of the surface forces plus the body forces plus any external forces on the fluid. So, this is surface force on the control volume, these are body forces, and then we have external force. Okay. Now, we will assume steady flow, steady rotational flow. Well, steady flow means that this will be 0, this integral will give you a 0. Okay. We will also assume that there are no body forces on this system. So, say this will also go to 0 then, all right. So, the momentum equation that we have would look like double integral of rho u dot n u ds, which we typically call as the efflux term, okay, the net efflux of momentum. So, that should be equal to the surface plus the external force. Now, I did not say anything about the contour C as of now. Well, the contour C could be of any shape, any size, but I am also free to decide or to choose a control volume C that exactly matches with the shape of the solid. What I mean by that is that if I could shrink this control volume down to match the shape of the solid in the, as a limiting case, that should also be valid, right. I can shrink C down to match the solid shape. In that case, if the contour can be shrunk, or if I choose a control volume which is really essentially the shape of the body, then the surface being stationary means that u dot n on the surface is 0. Okay, on this surface u dot n will be 0, and so this integral that we have here will also go to 0. It also means, by the way, u dot n is 0, it also means that the surface is a streamline. We should never forget this, and I will use this fact in a few minutes from now. Okay, so, the body is stationary, u dot n is 0. So, we can finally write our momentum equation as F s plus F external. Now, what was F external? F external is essentially the force on the fluid because of the presence of the solid, which would be, I can say, minus d I cap plus L j cap is 0. That is all we are left with. All right. Or we could say Fs is d I cap plus L j cap. Now, what is Fs? Now, Fs is the force on the solid because of the presence of the fluid. In our case, is from the pressure distribution. This is manifested as pressure distribution. So, notice that when you have an arbitrary shaped solid, you have pressure acting normally at all points, right? The fluid pressure acting in that fashion. So, we have P on the solid. So, F is essentially integration of all this pressure distribution on the surface to get the net force. So, what we can do now is to write the surface force Fs as a pressure integral. Okay. Now, pressure acts normally inwards into a solid. So, Fs is written as, so in this we will have a path integral because we are dealing with forces per unit depth. So, we will have an integral over the contour C of minus P n cap ds, okay, where ds is the contour path variable and n cap is the, of course, the unit normal at any given point, and we are writing it as minus P n cap, fully knowing that pressure is inwards. So, the effect, the pressure force is basically minus P n cap. Okay. So, just to remind you again what is ds, if you go back to the original sketch, we can say ds is maybe an element of this type. We are going around this contour. So, ds on an exaggerated sense is this element, okay. It is this small element which will go around, we will integrate over the entire contour to get this integral. Okay. And this integral should be d I cap plus L j cap. Okay. Now, so referring to this figure again now that I have drawn here, let us look at the infinitesimal element ds, okay, and let us try and resolve it into its projections along x and y axis. So, we have the element sort of like this is ds, okay, and I am going to try and resolve this into its projections along x and y. So, say this is the projection along y is dy, the projection along x axis is dx, and say the slope of this ds with the x axis is theta. Okay. Now, on this element ds, small element, pressure acts normally inwards. So, let me choose a different color for pressure. Let us say this is the pressure distribution on this element, infinitesimal element, this is P. Okay. The normal vector to this surface is pointing outwards, this is n cap, all right. For this element, the normal vector is in this form, okay. It is an outward normal. More importantly, normal vector, as this terms denotes, normal vector is normal to the line ds itself. Now, that comes in very handy for the reason that I can write what normal vector will be in terms of the angle theta. So, note that if this line ds makes an angle theta with the x axis, then the normal vector should make the same angle theta with the vertical axis, with the y axis, because normal being perpendicular to or being orthogonal to ds. So, when we resolve the normal vector into its two components, okay, say nx and maybe ny into the two components, we would say normal vector is nx I cap and minus ny j cap. Just in this case, for instance, ny is pointing downwards, or it is a projection on the negative y axis. So, I can say it would be nx I cap minus ny j cap. Now, nx, for the reason that normal vector has a unit magnitude, nx comes out to be, as you can see already now, hopefully nx will come out to be sin theta. So, we will have this as sin theta I cap as the x component, and the y component will be cosine theta j cap. More importantly, if I take the magnitude of n cap, you can see it would be square root sin squared theta plus cosine squared theta, which is 1. So, it is a unit normal. Okay. Now, I can also exploit the fact that the projections of this element ds along x and y are dx and dy. So, sin theta is basically dy by ds, right. So, this is dy by ds I cap minus cosine theta is dx by ds j cap. So, our normal vector to this element is given by this form. So, let us use this and substitute it here. Okay. Let us put it here. Let us see what we get. So, when we substitute, we will get d I cap plus L j cap to be minus p. We will have a dy ds I cap minus dx ds j cap ds, which I could write as, noting that it is a chain rule in ds as it appears, I can say this would be minus p dy I cap minus or plus p dx j cap, right. So, sort of getting rid of these terms. And so, now noting that if the equation has to be valid, then the individual coefficients of these orthogonal vectors I cap and j cap must be equal. So, I can say d, the drag force by unit depth, must be integral minus p dy over the contour C, and lift should be integral p dx, and that is a very powerful tool that we have come up with now. Okay. So, in this case, in the solid body, this is what the force should look like. So far we were using vector notation. Now, let me get to the idea of using complex potentials and the complex velocities. So, hopefully this is clear now. Okay. So, hopefully this part you have all been able to follow. Now, what we will do is we will construct a new complex function. So, say we construct a complex function given as the following. We construct a complex function which is d minus IL, where d is a drag force, L is a lift force. In terms of the integral, this would be minus p dy minus iota p dx, which I can also write as its integral over the same contour. So, I can say this would be p dy plus I dx. Okay. Now, note something very special here, that dy plus I dx, which I can write this as minus iota square dy plus iota dx, which could be written as, if I pull the iota outside as a common factor, we get dx minus I dy. Okay. So, if I say a complex number in the plane is z, which is x plus I y, then dz is dx plus I dy, and so the complex conjugate of dz, which is dz star, the complex conjugate of dz would be dx minus I dy, and this is exactly what this is, right. So, we can say dy plus I dx is I times dz star. So, d minus I L is minus integral of p, as I said dy plus I dx is I dz star. So, iota being a constant, we can write that this equation, if I have the pressure, should give me the force on a solid. Okay. So, this is the form of the complex force in our example. So, finally, we need to integrate the pressure distribution over this surface in a certain way, and that would give us the forces. Now, to integrate pressure distribution, we need to first derive the pressure distribution. So, for this we use again Bernoulli's equation, right, because the flow is a rotational, and we use the Bernoulli's equation to correlate pressure in terms of velocity on the surface of the solid. So, we can say that far away, because the pressure is some p infinity and the velocity is uniform, which we say as capital U. So, half rho u square, this must be the pressure on the solid plus half rho u square plus v square. Okay. That should be the form of the kinetic energy, and so clearly P should be equal to P infinity plus half rho u square minus half rho u square plus v square. So, we can substitute this pressure here, and then let us do a few steps to see what we get. So, we will get d minus I L to be minus iota integral over a closed contour. By the way, C is a closed contour, which is a very important part of this derivation. So, this would be P infinity plus half rho u square minus half rho u square plus v square dz star. Okay. And so, what we get is minus iota P infinity dz star minus iota half rho u square. Well, I can maybe keep it inside just to make a point here, that I can say this is integral of rho u square dz star plus, we can write the last term will be half iota rho u square plus v square dz star. Now, notice a few things. The contour C is a closed contour. If you start at a certain point, you will go around on the entire surface and reach back to the same point. Noting that, and also noting that P infinity is a constant, rho u square is a constant, the integral over of dz star over the closed contour will actually be 0. So, you basically you get to the same point. So, this function will be 0. Similarly, this function will also be 0 because rho u square is a constant. So, integral of dz star over the closed contour is again 0. You basically have the same initial and final points. The last thing I want to tell you is that u square plus v square, which is basically the square of the velocity magnitude, could be written as u plus iv into u minus iv. And we note that u minus iv is essentially our complex velocity. Okay. So, we will put this here. So, we can say that this will be half iota rho u minus iv u plus iv dz star. Now, we go to the surface of the solid again, and we look at this number u plus iv, which could be written as, well, u square plus v square square root, which is the magnitude of this function, into the argument given in terms of angle theta. So, if you think about what is this, we would say theta should be tan inverse of V by u, right, that is what it should be. But also note that since the surface is a streamline, it is a surface through which no flow can cross, then theta is also the same as tan inverse dy dx, right, that is the definition. So, this angle theta is the same as actually this angle that I had drawn here originally, the angle theta in this picture, which is parallel to the vector which is along line which is tangential to the surface of the solid at a given point. What I mean by that is, and this may be a little hard to absorb, but since I am saying since u dot n is 0 on the surface, then even if I write, for example, the dz function, the small increment in complex plane, which would be dx plus I dy, this would also be could be written as modulus of dz into e to the power iota theta, which further means that the complex conjugate of dz, which is dz star, would be modulus dz into e to the power minus iota theta, noting that the complex conjugate does not change the magnitude of the complex function, it only changes its polar angle. Okay. So, we are keeping a few things here. We are noting that the surface of the solid is a streamline. So, the velocity function, which is u plus iv, must be parallel to the element along the complex surface. These two angles must be in the same direction, noting that the surface is a streamline, and for a streamline we always say that dy dx, okay, along psi equal to constant is given as the ratio of v by u. So, we use this property now to simplify our integral. So, we write d minus IL, which was half iota rho over contour C, which we wrote as u minus IV, right, u plus IV, which I can sort of write as, or let us write it in this form, we can write this as u square plus v squared square root into e to the power iota theta. Dz star is modulus dz e to the power minus iota theta. Essentially, this is the integral that we have to compute. What I can do is I can rearrange this. By rearrangement, what I mean is I can put this here and this here. I can just move them, okay, from their places. So, I can say that this will be u minus IV u square plus v square square root times e to the power minus iota theta times modulus dz e to the power iota theta. Now, by doing this, what I have done is, if you look at this function alone, modulus dz e I theta, I hope it reminds you of something. Modulus dz e I theta is just the function dz, okay, the element on this curve in the complex plane. U square plus v square square root into e to the power minus iota theta becomes u minus iv, isn't it, right. So, we can get this as the integral as half iota rho over surface C u minus iv times u minus iv times dz, which could be written as half iota rho u minus iota v square dz. This is d minus IL. Now, note that u minus IV is the complex velocity W in the Cartesian system. So, d minus IL or the force on this solid would be given by the integral of w square, the square of the complex velocity over the surface C into half iota rho, and this is a very fundamental theorem that we derived, which is also, as I said, is called as Blasius theorem. Some books may actually call this as the first of the Blasius theorem. Right. Now that we have done all this complex analysis, so for any flow, if I know the velocity w on the surface of the solid, I could theoretically calculate this integral and be able to derive the drag and the lift forces experienced by that solid quite easily, and that is the beauty of this whole description and this whole method. Okay. So we will take an example of this in the next lecture, and then we will actually close this course with the discussion on conformal transformation. So hopefully this would have been clear, and as I said, we will definitely apply this for some special cases to show you that this actually gives you the right answer for the force. Okay, thank you.